Good morning, students. Yesterday we have completed magnetic field due to a circular coil carrying current at a point on its axis. We have got the equation B equals to mu naught divided by 4 pi 2 pi Ni r square divided by r square plus x square to the power 3 by 2. Then after this we come across current carrying loop act as a magnetic dipole. Current carrying loop act as a magnetic dipole. Wherever the existence of the magnetic dipole, there is the existence of what? Magnetic dipole moment. Our aim is to obtain the magnetic dipole moment due to a current carrying loop. So, consider whatever the equation we have derived yesterday, B equals to mu naught divided by 4 pi 2 pi Ni r square divided by r square plus x square to the power 3 by 2. Right? When I compare the distance of the point on the axis of a circular coil and its radius, here x is far greater than r. Here is x is far greater than r. Hence, square of the smaller values again too small. Hence, r square is neglected. R square is neglected. B equals to mu naught divided by 4 pi. I consider number of turns equals to 1. Let B equals to mu naught divided by 4 pi. I consider n equals to 1. 2 pi I r square. So, here r is neglected from the denominator. The neglecting term should be always either additive or subtractive. Do not neglect from the multiplication form, because if you neglect r square here, there will be no existence of the coil. When there is the existence of the coil, it must possess what? Radius. So, our neglecting term should be either additive or subtractive term. यहाँ पे addition है, यहाँ पे निकाल सकते हैं आप लोग. So, I remove this r square. बचा क्या? X square to the power 3 by 2 considered. N equals to number of turns. ये consider कर ले. I write it in systematic form. Shall I write it? Pi r square 2 यहाँ पे रख दूँ मैं. I as it is. Shall I write it? Pi r square divided by दोनों cancel हुए x cube. The area of a circle pi r square. The loop is nothing but what? Circular loop. Pi r square indicates what? The area of a circle. So, I can write here B equals to mu naught divided by 4 pi 2ia divided by x cube. I call equation number 1. गौर करो equation को. Then ये कहाँ पे magnetic field on the axis of a circular coil carrying current. Already हम लोग एक derivation करे सो है. The magnetic field, that is nothing but the electric field due to a electric dipole on the axial line and equatorial line. So, ये axis पे है, मैं क्या consider कर लेता हूँ मैं? Electric field due to a dipole on the axial line. But the electric field on the axial line A equals to, वहाँ पे क्या है? 1 divided by 4 pi epsilon naught 2p divided by x cube. Now I call this is equation number 2. Electric field due to dipole, electric dipole. This is nothing but magnetic field on the axis of a circular coil. Electric field on the axis of a dipole. दोनों compare करता हूँ मैं. Constant, constant. X cube, 2. Now this is nothing but electric dipole moment. Now this must be what? Magnetic dipole moment. I into A indicates what? So therefore magnetic dipole moment that is represented by M is equals to I into A. Shall I write here? Magnetic dipole moment M equals to I into A. So current carrying loop act as a magnetic dipole, and its dipole moment M equals to the product of current and area of a loop, and its SI unit is ampere meter square. Area is meter square, ampere meter square. देख लो एक बार इक्वेशन. Now this is the magnetic dipole moment M equals to I into A. So directly दे सकते हैं इक्वेशन. So equation कैसा आया? At that time we have to be once again back. पहले बता देंगे. First you have to remember only this equation. We don't ask these factors. So what is the magnetic dipole moment? M equals to I into A. It is a product of current and area of a loop. Is it clear? मैं इसी को हाईलाइट करता हूँ. ये पूरा तो है, कैसा आ गया? Then I go for this magnetic dipole moment. निकाल दो? Yes. I go for magnetic dipole moment. खाली लास्ट का जो स्टेप आया सो है, इसी को मैं कॉन्सेंट्रेट करता हूँ. Yes. Magnetic dipole moment. Magnetic dipole moment. Capital M. We know that अभी इक्वेशन प्रूव करे सो है, it is a product of current and area of a circular loop. So if I take the circular loop carrying the current I, when the current is passed through the coil either in clockwise direction and anti-clockwise direction, if the current is flowing through is it clockwise or anti-clockwise direction? Anti-clockwise direction. Then the face of the coil is act as a north pole. If the front face is acting as a north pole, what about the back face? Back face is acting as a south pole. Always the magnet exists in the form of what? Pairs. अगर if north है, पीछे का face क्या हो जाता? South हो जाता. Hence the current carrying loop act as a magnet. Now this is nothing but our bar magnet. One face is acting as a north pole, another face is acting as a south pole. Now this is our area. So magnetic lines of forces are originated from north and terminates on south. Now these are the magnetic line patterns. Hence we can say that current carrying loop act as a simply bar magnet. One face is acting as a north and another one is acting as a south. Hence magnetic dipole moment is nothing but the product of current and area of a loop. So we can conclude that the current carrying loop act as a bar magnet. Hence it consists of north pole and south pole. Wherever the existence of the magnetic dipole, there is the existence of the magnetic dipole moment M equals to I into A. Its SI unit is ampere meter square. Current is ampere, area meter square. Now this is the concept. Are you getting the point? Then after this, let me come across the main thing of the topic. One of the important thing in the topic, that is Ampere's circuit law. Circuit is nothing but closed path for the current. Shall I go for Ampere's circuit law? Yes. Ampere's circuit law. Ampere's circuit law. Ampere circuit law. Name of the scientist Ampere. He dealt with what? The detailed study of the current. The circuit is nothing but a closed path for current. So according to the Ampere circuit law, what he states? Now there are the integration. Now the integration is represented by the symbol like this. This is nothing but simply summation. The larger parts are summated with the easiest form, that is nothing. If I apply this integration for closed path, now this is a closed path. Now this integration is called line integral. This is called line integral. Are you getting the point? So I explain the term. This is nothing but what? Line integral. What is that statement? Ampere's circuit law states that the line integral of a closed path, the magnetic field due to a line integral of a closed path, the magnetic field due to a line integral of a closed path is equals to mu naught times the current through the closed path. So line integral of dl is nothing but length. That length is nothing but circumference, a closed path. The magnetic field due to a line integral of a closed path is equals to mu naught times the current through the closed path. So current is a scalar quantity. The dot product of the two vector gives what? Scalar. If I directly propose, यहाँ पे directly sign डाल दिया, directly proportional to, the proportional constant is mu naught. Nothing should be existed for that coil. Air should be surrounded it. That air is nothing but permeability, mu naught. That is a factor directly. The magnetic field due to a line integral of a closed path is equals to mu naught times the current through the closed path. Now this is called Ampere circuit law. By using this Ampere circuit law, we can calculate magnetic field due to a long straight conductor, we can deal the magnetic field due to solenoid, toroid, etc. To deal the things, to make the derivations easier, we take the help of what? Ampere circuit law. समझ में आ गया? The magnetic field due to a closed path, line integral of magnetic field due to a line integral of a closed path is equals to mu naught times the current through the closed loop. Right? A dot product क्यों है मालूम है? Current is a scalar quantity. The dot product of the two vector gives scalar. By using this Ampere circuit law, I go for magnetic field due to a long straight conductor of infinite length. ले सकता हूँ मैं. By using this Ampere circuit law, I go for magnetic field at a point due to a long straight conductor. Magnetic field at a point. Next derivation, magnetic field at a point. Magnetic field at a point due to a long straight conductor. Due to a long straight conductor. Long straight conductor. So yeah, right. Now this is the long straight conductor of infinite length, very large length. Unless until to pass the current through it, it cannot produce a magnetic field around it. Now this is the point P where the magnetic field is to be determined at a distance r from the current carrying conductor. So I want to apply the Ampere circuit law. I need the closed path. I consider the Ampere loop a circular loop where R acts as its radius and P lies on Amperean loop. And this is the direction of the magnetic field. And this is the direction of what? Length. So, sorry, magnetic field is always perpendicular to the point. Now this is the direction of the magnetic field and direction of dl. Both are in the same direction. Then what is theta? 0. B and dl are along the same direction. So, I want to calculate the magnetic field at a point P by using the Ampere circuit law. This is the Amperean loop. R is the radius of the Amperean loop, circular loop, and P is the point on the Amperean loop, where B and dl are in the same direction. We know that the line integral of magnetic field due to a closed path is equals to mu naught times I. Right? Then I solve this. Vector B dot vector dl, B dl cos theta is equals to mu naught I. Here theta equals to 0. Here theta equals to 0. Cos 0 equals to 1. Theta equals to 0. Therefore, cos theta equals to cos 0 equals to 1. So, B dl is equals to mu naught I. So, B is the constant, dl is equals to mu naught I. The line integral of dl for the closed loop, that is nothing but circumference. So, I come across here, B equals to integration of line integral of dl is nothing but, so integration of dl is nothing but L. If it is made the circular loop, that dl is length is nothing but what? Circumference, 2 pi r is equals to mu naught I. Right? Because line integral of dl is equals to circumference 2 pi r. So, I need the magnetic field B equals to mu naught divided by 2 pi current by distance. Now, this is our equation. Dekh lo. Now, this is the magnetic field due to a long straight conductor at a point P. It is obtained from the Ampere's circuit law. By considering the Amperean loop of radius r, the point P where the magnetic field is to be determined, which is at a distance r. एक बार पूरा इक्वेशन को गौर से देख लो. Right? Then I go for the second application of Ampere circuit law, that is nothing but we call it solenoid, the magnetic field due to solenoid. At the center of the solenoid and at the end of the solenoid. हम center निकालते हैं. सही है? Is it clear? Yes. निकाल दो. Magnetic field due to a long straight conductor B equals to mu naught divided by 2 pi current by distance. Now this is the distance r. Right? Then I go for solenoid. I go for solenoid. Then what is that solenoid? It has got the wide application. When you come across the water filter, we have got the switch on and off. In that switch on and off, we take the help of what? Solenoid. There are so many applications. बाद में applications देखेंगे. Then we come across solenoid. What is that solenoid? I take the long conducting wire. Now this is a long conducting wire of length L. एक wire ले लिया मैंने. Then I take the cylindrical base. Now this is the cylindrical base. I wound this wire on the cylindrical base. Right? Now this is nothing but a radius of the single coil. Now this is the length of the solenoid. Then how to define it? A long straight conductor wound on a cylindrical base. A long straight conductor wound on a cylindrical base whose diameter is less than its length, then it is called solenoid. A long straight conductor wound in a cylindrical form whose diameter is less than its length, then it is called a solenoid. Now this is your solenoid. If I remove that cylindrical base, it acts as a coil. आप cylindrical base को निकाल दिए. Now this is nothing but coil. Now this is nothing but your solenoid, which consists of a number of turns. A long straight conductor in the cylindrical form whose diameter is lesser than its length, then it is called solenoid. So when I pass the current through the solenoid, now this is the current flowing through the solenoid. Now this is nothing but anti-clockwise. One phase is acting as a north pole, another one phase is acting as a south pole. Hence, the current carrying solenoid act as a simply bar magnet. Simply this act as a bar magnet. The magnetic lines of forces are originated from north pole and terminates on south pole. The magnetic lines of forces are originated from north pole, terminates on south pole. Right? Hence, the current carrying solenoid act as a bar magnet. One phase is acting as a north pole and another phase is acting as a south pole. So, what is the difference between the bar magnet and solenoid? In the bar magnet, the magnetic field is maximum at the end and minimum at the center. And it is in the case of solenoid reverse. In the solenoid, the magnetic field is maximum at the center and minimum at the ends. That is practically evaluated. In the case of bar magnet, the magnetic field is maximum at the ends, that is maximum at the poles, and minimum at the center. But in the case of solenoid, it is reverse. The magnetic field is maximum at the center and minimum at the ends. So our aim is to calculate the magnetic field at the center of the solenoid. Then what is that magnetic field depends on? All these factors should be obtained when you go for the derivation. समझ में आ गया? What is that solenoid? Then the current is passed through the solenoid. It acts as a bar magnet. The difference between the bar magnet and solenoid is, in the bar magnet, the magnetic field is maximum at the pole at the end and minimum at the center. In the case of solenoid, it is maximum at the center and minimum at the ends. Right? Then I go for magnetic field due to a solenoid at its center. Magnetic field due to a solenoid at its center. Magnetic field due to solenoid at its center. At its center. Right? I take the solenoid. When I go for the magnetic field to analyze at the center, it is not possible by taking the coil. तो point अंदर आप नहीं रख सकते हाथ से. I take the sectional view. I take the sectional view of the solenoid, where it consists of a number of turns. Right? Now there are a number of turns in the solenoid. One phase of the solenoid acts as a north pole, another one is acting as a south pole. That north and south is represented by cross and dot. We have studied in the magnetic field direction. that is nothing but current through the circular coils in the first video. Now this is the sectional view of the solenoid. One face is acting as a north. North is represented by a circle with dots. Now this indicates what? The face of the coil is acting as a north pole. And another face is acting as a south. South is represented by a circle with cross. Is it clear? Now this is the axis of the solenoid. The magnetic field P. That is P is the point at the center of the solenoid. My aim is to calculate the magnetic field at a point P. मेरे को यहाँ पे निकालना है. Then I come across at the ends. So P is inside the what? Coil where the magnetic field is to be determined. Then I apply the Ampere circuit law. Now this is nothing but straight hai. Then I consider the loop. What is that nature of the loop? I take a rectangular loop. Now this is the rectangular loop. I call this is ABCD is a rectangular loop. Now the P is included in length AB. So now this is nothing but ABCD is a Amperian loop, so that I want to determine the magnetic field at the center of the solenoid. Are you getting the point? Then I go for from the Ampere circuit law, magnetic field due to a closed path is equals to mu naught times the current enclosed by the loop. Now this is nothing but the closed path, Amperian loop. I have to apply this. What? The integration for closed path for this rectangular loop ABCD. Then, therefore, I solve this one. I read A to B. I go from A to B. A to B. Magnetic field due to a current loop. Plus this closed loop consists of what? AB, BC, CD and DA. B to C. Magnetic field due to a current loop. Then C to D. सही है? प्लस बचा क्या? D to A. Is it a closed path? हो गया? Is equals to mu naught times. अब A निकालने के बाद पूरा फिर इसके ऊपर सर्कल मत डालो. We are solving that circle. The circle that is nothing but closed loop consists of A to B, B to C, then C to D and D to A. Here AB is parallel to the axis. What is theta? 0. Here perpendicular, BC perpendicular, DA perpendicular. But this DC is outside the coil. Hence there will be no existence of the magnetic field. So AB parallel to the axis. बाकी ये क्या है? BC perpendicular to the axis. BDL cos theta. अगर यहाँ पे सॉल्व कर दिया मैंने, BDL cos theta is equals to mu naught I. This is my base. इसी को मैं बेस कर लगता हूँ मैं. अब यहाँ पे सॉल्व कर दे BDL cos theta, BDL cos theta, BDL cos theta, BDL cos theta. यहाँ पे BC perpendicular to the axis. Hence theta equals to 90 degree. This is outside. There will be no existence of the magnetic field. Again it is perpendicular. बचा कौन सा? अब AB is only parallel to the axis. Theta equals to 0. Therefore, right? Now this is having the length L. सही है. So I solve this. बाकी पूरे कैंसिल हो जाते. These are nothing but cancels. Perpendicular. Now this is outside the coil. The magnetic field is 0. Again it is perpendicular to the axis. So cos 90 is 0. These are get cancels. This is the parallel AB. BDL cos theta cos 0 equals to BDL. So I solve this. integration of dl A to B, that is nothing but length L mu naught I. This is B into L mu naught I. So yeah, but it consists of how many turns? N turns. For N turns, B into L. Current is flowing in a number of turns, hence mu naught I multiplied by N. Therefore, B equals to mu naught N by L into I. Number of turns per unit length, B equals to mu naught Ni. This is your equation. Number of turns per unit length, that is nothing but small n, B equals to mu naught Ni. Is it clear? देख लो पूरे स्टेप्स, और हो सके तो इसको यहाँ पे थोड़ा दूर लिख दो मैं n by L ले स्पेसिफिकेशन के लिए. Therefore, B equals to mu naught Ni. सही है? Because n by L is equals to small n. This is magnetic field due to a solenoid where the magnetic field at the center B equals to mu naught Ni. Simplest derivation. आपके नोट्स में पूरा है कैसा जीरो है बोल के, right? So this gives what? Magnetic field at the center of the solenoid. If I want to calculate the magnetic field at the end, the magnetic field at the end of the solenoid, I call this is B dash. Now this is here B. Practically it is evaluated. The magnetic field at the end of the solenoid, B dash equals to half of the magnetic field produced at the center. This is nothing but mu naught Ni divided by 2. Mu naught Ni divided by 2. This is the magnetic field produced at the end of the solenoid. Mu naught Ni divided by 2, the maximum at the center and minimum at the ends. What is the magnetic field at the end of the solenoid? Half of the magnetic field produced at the center. Now these are about what? Magnetic field due to solenoid at the center and its end. Right? I hope that you have understood the class. The next we come across its next extension version, that is called toroid. Right? Shall I continue with the next class? Starts with toroid? Okay. We end the session here. Thank you.